All right. I suppose in the interest of time, we should go ahead and get started. I'm guessing folks will trickle in as talks get going. But thanks to everyone for sticking around for the last session of the conference. I think we've got four really great papers lined up here on kind of energy efficiency policies, kind of broadly defined, and I'm really excited to see them. So let's just go ahead and get started and not take up any more time. We'll go ahead and start with Dorothée Charlier presenting on heating externalities.
Yes, I share my screen. Okay. So thank you very much. I'm very glad to present to you a working paper. It's a joint work with Louis-Gaëtan, Giraudet, about heating externalities in multifamily housing and the impact of externalities and the type of energy billing on heating energy expenditures in the French residential sector. Why we decide to focus on this type of subject is because we note that it exists some heating externalities and more specifically heating losses in a collective building. It's possible to have some vertical losses and some horizontal losses according to the floor where you live. For example, if you live in the ground floor, the heat go to the top, and it's possible to have some losses. So we have some basic physics, and today we note that it can move across adjacent dwellings, and it's possible to have some losses between dwellings according to the floor. So, according to this fact, in France, we have a lot of collective buildings because multifamily dwellings represent nearly 14% of total building stocks. And moreover, we have a lot of collective building with collective intake system. That is to say, we have only one type of intake system, it's the central heating system for the whole building. Moreover, we have different types of utility contracts in France. It's possible to have an individual billings, or it's also possible to have a collective billings where the price signal for each household is not very clear. And according to these facts, we would like to know if we have some different type of expenditures according to the level of the floor where you live and the type of billing that you have. Moreover, the obligation in France is evolving. For example, since 2017, we have a lot of dwellings where it is become mandatory across Europe to have some individual billings. But individual billings can be fair if we consider that does not exist some vertical or horizontal heat losses, for example. And we have almost 1.8 million dwellings occupied by 6 million individuals were subject to this obligation of individual billing in France. So to our best knowledge, the economic significance of heating externalities and how heating externalities can diminish the effectiveness of implementing individual billing has never been assessed. So in this paper, we would like to know if it exists some heating externalities and what is the magnitude of these externalities. We want to know if the fact to live to the ground floor or to the last floor can lead to some overconsumption or extra expenditures. And we would like to know behind these two phenomena if some type of households can be more vulnerable according to the type of the floor where we live. So in order to conduct this survey, we use a French database from 2013. Unfortunately, we are still waiting the last wave of the survey. And we have a sample only for households living in multifamily dwelling, and we can observe 10,000 households. And in this database, we have a lot of information about the building, but also a lot of information about the socioeconomic. So we know the rent, the income, but we have also some information about the quality of the buildings. When I talk about quality, I want to say energy efficiency. So for example, we know the period of construction, we know the type of heating, and if we have a central heating or an individual heating. We also know the exposure of the dwelling and the surface area, etc., etc. And we have also information about where the dwelling is located in France and where the dwelling is located in France in order to have a proxy for the heating need in winter. So to give you some statistics about this database, we have in France, in average, an average energy expenditures around 955 euros. But this average can be very different according to the type of the dwelling and more specifically according to its energy efficiency, because the standard deviation is quite important. About water expenditures, and I present some statistics about them because we can compare behavior according to energy expenditure and to water expenditure, especially in the case where utilities are included in the contract. In France, water expenditure in average represent less than 100 euros per year. Which is interesting is to have a big picture about the repartition of households according to the floor where they live. We have nearly 15% of households living in the ground floor, 21% of people living in the last floor, and a great majority of households live in the intermediate floor. In France, we have also nearly 14% of households who have the heating expenditures, including in their utility bills. And we have also the same phenomenon for the water expenditures. It represents 23%. One another interesting fact is about the repartition of households according to the floor. What I want to know if we can consider there is a random repartition of households according to the floor, or can we have a huge majority of poor people living in ground floor compared to the other floor? That we can observe is, firstly, in average, the rent for last floor is greater than the rent for ground floor. And we have the same type of conclusion if I take a look to the dwelling price. Dwelling located in the ground floor are cheaper compared to dwelling located in the last floor. That is to say, it seems reasonable to think that it's not the same profile of households that live in the ground floor compared to the other floors. Moreover, if now I just take a look to heating expenditures, to the first column in the table, I can note that in average, 18 expenditures for the ground floor per year is greater than 18 expenditures for people living in the last floor. So that we want to see if this conclusion is due to 18 externalities or to other factors. What I can also note when I take a look to descriptive statistics is due to the magnitude of 18 expenditures according to the fact if charges are including or not including in the utility contracts. And it's quite obvious when I take a look to the feature to this figure is the fact that people living in collective building where charges are included in the utility contracts spend more for energy than people where charges are not included. That is to say, we have very important differences in terms of energy expenditures if you face to an individual billing or to a collective billing where you don't really know the cost of your energy consumption. So now what I want to estimate is how energy use varies across floor designation, and I want to know if we can really consider various different energy expenditure ceteris paribus according to the level of the floor. And I will compare differences in energy expenditures to differences in water expenditures, because when I just take a look to water expenditure, I do not expect that the floor can have an impact on water expenditures because there is no heat losses. In order to quantify these energy expenditures, I have a lot of methodological issues and challenges, especially due to endogeneity. I face two sources of endogeneity. I face one type of endogeneity due to the choice of the equipment, the energy used, due to the performance. And I face to another type of endogeneity due to the type of the floor where you live, because like I said previously, the floor where a household lives is not random and it depends to its socio-demographic characteristics. So in order to consider these two sources of endogeneity, I will use a conditional demand analysis set work, that is to say a type of two-state discrete continuous choice model. That is to say, I consider there is selection in the first step. This selection is the selection for the type of the floor and the type of the equipment. That is to say, when I decide to live in a dwelling, first, before consuming energy, I know I choose a level, I choose a floor, and after that, I choose an equipment. And according to my previous choices, I decided how energy to consume. So to address this endogeneity problem, I need to find some instruments. So I need to find instruments to modelize the choice of equipment, and I need an instrument in order to modelize the choice of the floor. And to our best knowledge, this is the first time that we consider a potential endogeneity issue due to the floor choice. So in order to instrument the heating technology, I will use a common instrument already used in the energy consumption literature. So I use the connection to the gas network and the size of the urban unit. Why I use these two instruments is because they can explain the performance of the equipment, but they cannot explain after that the energy expenditures. The connection to the gas network is mostly in the big cities and not in rural area. In order to instrument the choice of the floor and an instrument who do not have an impact on the energy expenditures, I use the presence of an elevator. Elevators are mostly in the most recent building. And when I want an elevator is also because of other factors, for example, unobserved health condition, if you have some children, or other considerations. And we also introduce number of units in the dwelling. In order to be sure about the quality of my instrument, I also use a lot of empirical tests in order to be sure about the quality of the identification and the exogeneity of the instruments. So I decide to estimate the total energy expenditures as a function of household characteristics, dwelling characteristics, and also according to the choice of the floor and to the choice of the heating system. And the choice of the heating system and the choice of the floor are also due to household characteristics and building characteristics, but are also depending on the different instruments that I'm just presenting. In order to estimate, so we have a system of three equations, and in order to estimate this system of three equations, I do not use two stages least square model, but I use an extended regression model where it's possible to have a simultaneous system of equation, and results are better because the predicted value for energy expenditure that we obtain is closer with this method to the observed value. So my main results show in the first steps that it is interesting to consider these two sources of endogeneity because error terms are correlated. So taking into account the fact that the choice of the floor is not exogenous is the first result. Second, when I consider the impact of the choice of the floor on the energy expenditures, if you take a look to the fourth column, the last equation where I control for the two sources of endogeneity, I can note that living in the last floor compared to the ground floor led us to decrease to 20% energy expenditures. And if you live in an intermediary floor compared to a ground floor, energy expenditure are 41% lower. So there is a significant impact of the floors and in consequences of heating externalities on energy expenditures. We compare, if you take a look to the fifth column, we compare our results about floors on energy expenditures and on water expenditures, and we do not have an impact on the floor on water expenditures. So it confirms the existence of vertical losses. Finally, in dwellings where heating expenditure are included in utility contracts, we have an important over energy expenditures, and this overconsumption is 73% in average, and it's very robust according to the type of the frame ropes that we use. And we obtain the same type of results if we do not consider that it is heating expenditure that is included, but when it is water expenditures included in collective billings. So if, just to sum up these results, when expenditures are included in utility contracts and when there is no price signal about your energy consumption or your water consumption, households overconsume.
You've got about 2 to 3 minutes left.
Yes, just the time to conclude.
Perfect.
So just to sum up what I said, energy expenditure are higher for households living on the ground floor. And remember, people living in the ground floor are mostly the poorest people. And that is to say, poorest people live in the ground floor and face to higher energy costs. And finally, living on the middle floor decreases energy expenditure by 41% compared to households living on the ground floor. In this case, overheating seems necessary for households living in the ground floor to maintain a desirable temperature in dwelling in these types of dwellings, and we can face to problem of fuel poverty. Because if you don't want to maintain this desirable temperature, it's necessary to decrease your energy consumptions. And finally, households that cannot control heating and that enjoy utility included contracts have a 73% higher energy expenditures. So we have a moral hazard problem. So what type of recommendation and what type of solution face to this type of results? One way is maybe to promote two-part utility contracts. One part which is a fixed part and designed to address these externalities. This part is set to 30% today in France. And it's really necessary to ban in utility including contracts because we know that the effect of utility including contracts is higher than the effect of heating externalities. And finally, one last maybe recommendation can be to have in mind that people living in ground floor are more subject to overconsumption. And it is necessary to isolate not only the wall, but also between the different floors. Thank you very much for your attention, and I answer to your question.
Great, thank you. Do we have any questions for Dorothée? If so, feel free to just unmute yourself, or you can raise your hand and I can call on you. Well, I'll take the chair's prerogative and ask a question. Start by asking a question, which is, it seems like this setting where you're going from utility included contracts to individual contracts is actually kind of replacing one market failure with another. The first market failure is this kind of principal agent problem, and then even when you're paying for your own energy, if your energy is spilling over to your neighbors, essentially, then you're kind of providing this positive externality that's not being, that you're not getting paid for. And so I guess I'm wondering if you can actually put some welfare numbers, instead of just saying it's a welfare improvement, if there's some way to put actual welfare numbers on each of these market failures to try to compare the two. Just kind of like in terms of magnitudes.
Yes, we would like now to go further in this analysis in order to have an idea what is the best policy, because if you have only individual buildings, it could be unfair because people living in the ground floor can overpay for their consumption. So what is possible to do for them? And after that, if we maintain the utility contracts and people who share their energy consumptions, we have a loss of energy. So it's really difficult. One way could be to improve the energy efficiency of the building in first way, because if ground floor are better insulated in the future, it could be a way to avoid some losses. But now in this we have to demonstrate that, and it can be also hard analytically that energy consumption is a sufficient statistic of welfare.
Great, thank you.
Thank you.
Do we have any other questions?
Yes. Can I ask a question?
Yeah, absolutely.
Yeah. Okay. Thanks for your work. I had a question about your instrumental variables, and I didn't well understand why do elevators are exogenous with energy consumption? Because if there is an elevator, the cost of the apartments will be higher, so it is really correlated with higher incomes people living in, and so higher energy consumption, to my mind.
Not really, because when I talk about energy consumption, is energy consumption only for heating.
Okay.
So according to me, having an elevator in a building, it's maybe to have an extra energy consumption for the elevator only, but not for your heating.
Yeah, but I mean, if you choose to live in a building where there is an elevator,
yes,
it means that you have the mean to buy or to live in a building where there is an elevator. So I mean you're in the top income classes. I mean.
yes.
And it is kind of there is several studies that tend to show that people with higher income consume more than people with low income in terms of heating consumption in energy.
Yes.
Even though there is no relation with the elevator consumption, but only for the heating consumption, they tend to consume more.
Yes, but in fact, first you choose your dwelling according to the heating technology and the fact you have and the level of the floor, and we control using elevator and other type of characteristics. And once you have choosing your dwelling and considering the level of the floor where you live and the type of technology you have, it's a type of theoretical energy efficiency. You decide how energy to consume. Okay. But there is no direct link between the choice of the floor, the elevator, and direct or real energy consumption. It's a proxy of theoretical energy consumption.
Okay. Thanks.
All right. I think we probably need to cut it off there for the sake of time, but let's thank Dorothée for a great talk and also for some good discussion here afterwards. And we will move on to the next talk, which is, let's see, we've got Cristina Peñasco presenting on dynamic treatment effects in energy efficiency.
Thanks a lot. Do you see my screen?
Yes.
Okay, perfect. Well, thank you very much for giving me the opportunity of presenting this work here today. I'm Cristina Peñasco. I'm an assistant professor at the University of Cambridge, and I will present it work in progress and preliminary results of joint work with Professor Laura Diaz Anadon, also at the University of Cambridge, on effectiveness of energy efficiency measures in the residential sector in the UK through dynamic treatment effects. I will start with motivation to move to the literature review, the hypothesis, the methodology, well, the normal type of outline. So improving energy efficiency is vital to ensure sustainable, affordable, and secure energy system. The residential sector represents on average almost 20% of the total final energy consumption in OECD countries. And this reached one of the highest percentages in the UK, with 29.5% of the total final energy consumption. More and more, it is assumed that reducing energy demand through greater efficiency can help the UK meet its climate and energy efficiency targets, reduce energy bills, and fight fuel poverty, among other benefits. And in order to meet these climate and energy efficiency targets and so on, the UK has put in place several energy efficiency related policies, as summarized in the figures. However, policymakers are not achieving the results expected from the implementation of these policies in buildings. The UK government has set up heating and housing benefits that may influence both the energy consumption and also the expenditure of households. And the focus of those policies has been mostly vulnerable households. The UK government presented actually in September 2020, the last scheme is the part that you can see here, called Green Home Grants. And the goal pursued by the UK with this program was to improve the energy efficiency of over 600,000 homes, but they had to cancel the program because people didn't use it. So while UK government keeps investing in energy efficiency technical measures, research is not conclusive about the effectiveness of retrofitting measures in transforming 100% of the saving potentials, mostly due to the impact of the rebound effects associated to occupant behaviors and the lack of engagement with the instruments. So the aim of this paper is to shed light on the extent to which technical energy efficiency improvements, specifically the installation of loft insulation and cavity walls, are associated by changes in residential gas consumption. More importantly, this paper analyzes the dynamic effects of the installation of such measures and the lasting effects of energy consumption reductions. It also assesses the degree of sensitivity of household energy consumption to changes in prices and the groups that benefit from energy efficiency measures, with the goal of understanding how to design better policies to reduce residential energy use. With this paper, we contribute to the available evidence in different ways, or we expect to contribute to available evidence in different ways. First, with an analysis of gas consumption patterns in the UK at the micro level for a large panel of households of more than 50,000 dwellings. In that case, it's important to take into account the specific as well consideration of gas consumption, that is energy used for heating. But however, probably one of the most important contributions is the analysis of the long-lasting effects of the energy efficiency technical improvements in residential buildings, with a segmentation of the sample to understand the role of two things: other renovations first, and the vulnerability of the households second. I won't stop here long because this is something well known. So the framework for studying energy efficiency is as old as the Gibbons paradox. The Gibbons paradox states that in the long term, an increase in energy efficiency in resource use, in this case, energy or gas specifically, will generate an increase in resource consumption rather than a decrease. And in economics, this has been traditionally analyzed in terms of rebound effects. The literature has been very prolific in exploring the impact of households' energy efficiency technical improvements on energy consumption, with ex-ante assessments using different techniques, including general equilibrium models, macroeconomic demand models, and systems, input-output models. Actually, one of the last contributions in the UK regarding the potential of energy savings in households has been Rosno in 2018, who estimate the lifetime energy savings associated to different level of deployment of energy efficiency technologies up to 2035. But with notable exceptions, we found that there is a gap in the literature in terms of the ex-post evaluation, what really happened after the changes in residential energy consumption happens, and that follow the implementations of the different energy efficiency technical improvements. The evaluation of actual energy savings in the UK and the factors that may influence the energy consumption or the impact of different energy efficiency measures is very timely, particularly given, as I just mentioned, the perceived policy failures in the residential energy efficiency space. There is significant research on the factors determining the adoption of energy efficiency measures, but research has found that there is no conclusive evidence detailing the extent to which differences between expected energy savings and realized one may be related to social challenges, like, for example, vulnerability or consumer resistance, or if it may be caused by rebound effects of policy-induced improvements. In addition to the rebound effects, many energy efficiency measures are implemented alongside other home improvements that may have associated increases in energy consumption, such as, for example, extensions, which are super popular in the UK. The combination of this old housing stock in the UK, the rebound effect, and the possible correlation between energy efficiency measure implementation and other building work may lead to increased energy use when taken all together. In addition to that, the literature indicates as well that we may also expect differences in energy consumption of households after adopting a particular measure for different income levels. So, for example, previous studies have observed higher rebound effects, of course, in low-income households for improvements in heating technology. And understanding energy consumption response in these different type of households, let's say vulnerable versus more rich households, is essential for policy making, as most of the energy efficiency programs have focused specifically on vulnerable households whose energy efficiency rebounds are expected to be higher than from other groups. So accordingly, we propose the following hypothesis related to potential reduction in household energy consumption after the installation of energy efficiency measures. The first one is that the installation of energy efficiency technical improvements, remember that we are talking about, in this case, loft insulation and cavity walls, is not enough to generate significant reduction in the amount of gas consumed by dwellings versus those that have not adopted them. The gas consumption reduction of households in the UK after the installation of an energy efficiency technical improvement, if any, does not last in time due to factors unrelated to the effectiveness of the technical measures. The third one is that households installing energy efficiency technical improvements alongside other renovations in dwellings do not experience significant energy consumption reduction. And the last one, which is related with these vulnerable households that we just mentioned. So vulnerable households installing energy efficiency technical measures do not reduce their energy consumption. Methodologically speaking, we will use a staggered differences approach with dynamic treatment effects. And we analyze with this changes in residential gas consumption before and after the adoption of the energy efficiency measures in an event study design. The analysis includes households' technical energy efficiency interventions subjected to energy efficiency programs in England and Wales between 2005 and 2017, using a panel of more than 55,000 households from the National Energy Efficiency Data Framework of the UK. I just mentioned we comprise two different interventions, loft insulation and cavity wall. And to the best of our knowledge, this is the first study analyzing energy consumption patterns in the UK at the micro level with this large panel of households of more than 50,000 dwellings and 700,000 observations. Not sure if the size is large enough, but well, we control at the micro level for dwelling size, the age of the dwelling and the type of dwelling. We take into consideration as well the region in which the dwelling is located by introducing regional differences in the unitary gas prices and in the weather conditions. So we basically normalize by region. We also account for the vulnerability of the households, which we approximate by using the index of multiple deprivation. We segment our sample to understand the role of the role played by other renovations delivered alongside energy efficiency improvements that we have to approximate with the variable conservatory, which is if the household has a conservatory or not. That means more than this kind of extensions in which more than 50% of the surface is glass. And we also, as I mentioned, segment the vulnerability of the households to derive policy implications that may help the UK to comply with climate and energy targets. As you can see from the next slide, we need to control for all those variables, as the households in the control group and the treatment group seems different in nature. This is just to show the number of households that have adopted some type of energy efficiency measure in the period of analysis. So as per 2017, almost 20,000, so it's 18,930 household has received some kind of treatment, loft insulation, cavity wall, or both. In terms of the methodology, so for most of quasi-experimental applications of differences in differences approaches, the method, as you know, comprise two groups, the treatment and the control, with two different periods, before and after. In this paper, the installation of the measures differs in time, that is households carried out. The energy efficiency improvement is different depending on the household and differs by years. Then the aforementioned canonical approach of the differences in differences is not valid. We need to generalize. The energy efficiency improvements are implemented, as I just mentioned, at a particular point in time that varies depending on the household at hand, and each dwelling will remain exposed to this treatment afterwards. For a regular generalized differences in differences, we would only allow for treatment effects heterogeneity in terms of the observed covariates and time. That is, every household become treated at some point and point T at a time when the first energy efficiency measure is installed, and that time varies across households. So in the first application of the analysis, we won't consider dynamic treatment effects. We'll just see the effects what happened before and after, allowing the possibility of having some effects post-intervention. In the second approach that we follow, the staggered differences in differences, we identify and estimate the effect of the treatment uses this generalization with multiple time periods, and also with these dynamic effects, holding uncontrolled for other possible confounding variables. Cerulli and Ventura have developed this estimation methodology to the case of binary time-varied treatments with pre and post intervention periods. We will use this development to analyze the differences in energy consumption 5 years before and 5 years after the implementation of the energy efficiency improvements. With this approach, we can not only analyze, as I mentioned, the effect of the energy efficiency improvement, but also if they have some anticipatory or delay effects. And this second quasi-experimental exercise allows them to analyze the extent and duration of the effectiveness of the implementation of the energy efficiency measures in the reduction of the energy consumption. I won't show it here because we won't have time, but we have performed some sensitivity analysis as well with different leads and lags periods in order to see if the results that we get were robust enough. So far, what we see is that energy efficiency technical improvements in households are effective in reducing the energy consumption on those households undertaking these measures. With the generalized differences in differences approach, but without dynamic treatment effects, we see an average treatment effect on the range of 6% for loft insulation and around 12% for cavity walls after the installation of the different measures. However, a new challenging and policy relevant result arises, and that is that energy efficiency effects derived from the installation of technical measures fade away around 1 to 4 years after the treatment. Cavity wall insulations generate for our preferred model with covariates and observed reduction on gas consumption in the range of 6.9, 7.8% in comparison with the pre-treatment period. The effect shows, as you can see in the slide, a decreasing pattern, and the effective reduction in consumption only lasts 1 more year after experiencing this rebound. For the second period after the treatment, the observed gas reduction varies on the range between 2.6, 3.7, and after 2 periods, the effect fades away, suggesting that behavioral interventions are needed as technical, in the same way as technical ones, if our goal is to get long-lasting energy efficiency gains. In the case of loft insulation, it seems to be half effective than cavity wall insulation, with the reduction on gas consumption on the range of 4% for the first period here, 1.8 in the second, 0.8% on the third, and unlike cavity wall, the reforming loft insulation effects on gas reduction seem to last a little bit longer, but it fades away again after 2-3 periods of after the installation. You can see that, but it's basically the table with estimations. I prefer just to show the graphs because it's more friendly, I think. We tested the idea that the households installing energy efficiency technical improvements alongside other renovations do not experience significant energy efficiency consumption, significant energy consumption reduction, sorry. What we see is that for those households, all the reductions happen during the first year. There is no reduction in the second year, and both interventions are having very similar impact with a reduction of around 5%. But certainly that is not long-lasting. However, the randomness on consumption that we saw at the beginning, it's somehow mitigated after the treatment, and this result is of special importance for the UK, where conservatories remains one of the most popular modifications to a property. That was the result, sorry, for loft insulation, for cavity wall, and after without conservatory, the results are similar to the previous one, to the general sample. Attention must be paid to the fact that the impact of the adoption of these measures varies considerably depending on the level of deprivation of the area in which households are located, from more deprived to less deprived areas. The particular lower effect on the poorest segment of the population, proxied by quintiles level of the index of multiple deprivation by area, may provide a rationale to focus the attention on the barriers that may prevent those households to get potential energy savings. So for households, for example, in the highest deprived area, the reductions are half of those in the lowest deprived areas, with 2% here versus 5% for loft insulation, and 4% versus 7% for cavity wall. Here we have the whole or any type of installation. On top of that, the medium-tier deprived areas are the ones that most benefited from the energy efficiency reduction from a technical point of view. We analyze also with percentile shares the proportion of total gas consumption in this case that go to different groups defined in terms of the relative ranks in the distribution when they install the energy efficiency measures. And what we see in that case is that an increase in consumption and energy happens in all households in lower percentiles, and it's only after the 40 percentile that the reduction in energy consumption actually happens and are effective. That is an important result. Well, this is the relative difference. You can see the graph as well.
You're about 3 or 4 minutes left.
Okay, thank you. We have done a robustness check with propensity score matching. Basically, we get that the variables or the treatment and control groups are much better after the propensity score matching. The results are consistent. Basically, what we see here is that the distribution then gets a little bit closer, but we confirm that the loft insulation, again, there is an impact in the year of the installation, with cavity wall the same, but the results fade away at some point. So just to finish then, the results in this paper confirms that energy efficiency technical improvements are effective in reducing energy consumption in those households that undertake the measures, but energy efficiency effects fade out and are not long lasting, and energy efficiency gains disappear around 1 to 4 years after the treatment. We test the idea that the households installing energy efficiency technical improvements with other renovations do not experience significant energy consumption reduction. And this hypothesis is actually only partially confirmed, as we find that reductions happens only the first year, but the pattern improves the randomness in consumption in those households with conservatory, which can be related simply with the idea that this has 50% of the surface covered by glass. And lastly, vulnerable households installing energy efficient technical measures don't reduce their energy consumption, which is confirmed, as those in vulnerable areas experience much less reductions. And in addition to that, those ones already in the lower percentiles of the distribution of gas consumption increasing their consumption after adoption of measures. That is good in the sense that this can have an impact on fuel poverty, but it's not the main goal of these energy efficiency policies in a sense. So we can derive several policy implications. There is a lack of effect on the poorest segment of the population, which may provide a rationale to focus the attention on the barriers that may prevent those households to get potential energy savings. Energy efficiency policies may be having a positive impact on reducing fuel poverty, as I just said, but the energy efficiency schemes are not effective in this segment. We also need to establish more tailored energy efficiency policies adapted to individual characteristics of households. Technical measures are effective in the short term, but not that much in the long term. Results highlight then that there are specific difficulties in the British housing stock associated to the high natural gas penetration and the traditional existence of conservatories in households that may be counteracting the positive effects. Therefore, we hypothesize that the implementation of energy efficiency schemes consisting of a mix of regulatory instruments or financial instruments as well, but together with soft instruments that foster behaviors that may make the energy efficiency long-lasting are needed. Further exploration, where we are trying to do quantitatively multiple treatments, adding the two of them together, and certainly qualitatively. We are not able to distinguish which are the behavioral aspects with the data we have. So we are now running a survey with UK households to explore behaviors and actually what is happening behind the results that we find. Thank you very much. And any question or comment are welcome.
Great, thank you, Cristina. Do we have any questions?
Yes, this is Bill Kemp. I'm coming up next, but I do have a question on this one, Cristina. So is the bounce back purely behavioral, or are the residents doing anything physically to their dwellings? I mean, are they just playing with the thermostat, do you think, or what's your hypothesis there?
So we think that there is this reduction when they adopt in the moment, but what we see is like actually the period, the long-lasting period, is only the period in which the household is the payback period. Okay, let's see in that way. So the payback period that has been calculated initially for a cavity wall or a loft insulation is exactly this 2 to 4 years. And after these 4 years, they come back to the normal levels. And we don't really know if that is the case. What we hypothesize is like the technical measure works because it generates this decrease, but the behavioral aspects don't long last after, and that is why they don't continue in time. We don't have variables at this right now to check if that is the case with this database specifically. Yeah, basically that is the reason why we are running this survey, try to figure out if this is that. The technical measure seems to work in the year, but we don't know what happens after, and it's kind of a black box as it is right now.
Yeah, well, for heating, at least you probably will be able to get some data from smart thermostats and so forth, and be able to track their behavior about the set points in the dwelling before and after the measures and so forth.
Yeah, there is some information, I think, in London Borough itself. So they put in place some smart meters projects and experiments in that sense. So we are exploring that as well. But we wanted to have something more representative for the whole population of of England at least. So that's why we have not focused specifically in London at this stage, but yeah. Thanks.
All right, I've got a question for you, Cristina. It was I found it really interesting to see the different effects across I guess that was deciles of gas consumption. Is that what it was? And it was positive for the low consumers and negative for the high consumers. I guess I'm wondering if you have any evidence that there are other energy efficiency measures being undertaken at the same time, that like the big consumers are going to be big households or wealthy households that might be doing kind of whole home renovations all at once, and that could be leading to some of the effects here.
Yeah, we don't have the information. There are a lot of different measures at the same time in terms of both gas and electricity. So most of these households, the big ones as well, that perform these renovations. And in terms of electricity consumption, what we see is that most of these renovations, and this is coming from a separate project as well, but most of these renovations are basically based on removing walls, extensions, which it will increase, for example, the level of electricity that they expend, and it's more difficult as well to heat places with bigger spaces or taller roofs. Certainly that can be the case. There is renovation. There used to be a shorter version of this data set that includes more energy efficiency measures, not only cavity wall and loft insulation, but it's not representative for the whole population. And that's why we decided to constrain ourselves to these two. This other database includes changing boilers, changing switching type of systems, lighting, of course, and all these things that we cannot see in this one. We constrain ourselves to gas specifically in order to avoid these other measures that are more related to electricity consumption, but it can be definitely related to that. However, what we see as well is that the households that are more efficient, but I think it's something that we all know in patterns of energy demand and so on, is the central tiers of the distribution. So the ones that are more efficient is always third, fourth kind of quintile, while the last ones are less or are more inelastic, and the first one are more inelastic in different directions. But yeah. Thanks.
Yeah, thank you. All right, we've probably got time for one more question for Cristina. All right, well, if we don't have any more, I'm sure she's happy to take questions and comments offline as well. So thanks again, Cristina, for a great talk. And let's see, next up, we've got Bill Kemp, and I think Natallia Pinchuk is going to be joining him on this talk as well. So Bill and Natallia, take it away.
All right, let me share my screen. Can you see that?
Yes.
Put it on slide view. All right. Thanks, Matt. My name is Bill Kemp. I'm a director in Roland Berger. I'll explain who Roland Berger is in a minute. I'm joined by my colleague, Natallia Pinchuk, who was really the principal investigator on this research and analysis. And I will be giving sort of the front end background and the results at the end. And Natallia will walk you through our analytical approach. It's good to be back before my colleagues at the IAEE. Just to date myself, the first one of these international conferences I attended was in 1984 in San Francisco. So it's been a while. I was hoping this one would be physically in Paris, but as we say sometimes longingly, next time in Paris. So I'll say that again, next time in Paris, but physically next time. So Roland Berger is a large international management consultancy, and Natallia and I are leaders in their energy practice in North America. We're both longtime consultants to the energy industry and related stakeholders. So unlike most of the IAEE participants, we're not academic economists, we're more sort of practitioners of applied energy economics, I would have to say, for our clients and other interested people. So with that background, so what I will do today, and Cristina had an interesting introduction or counterpoint to this as far as some of the assumptions that are implicitly embedded in our methodology here, but I guess we're assuming some permanence of savings. We're summarizing two studies here, Pathways Phase 1 and Pathways Phase 2, which were both conducted under the sponsorship, I'll be upfront about it, under the sponsorship of the gas industry in the United States, the gas distribution industry, the American Gas Association and the American Gas Foundation, its educational arm. They came to us in 2018 and were frustrated that nobody was talking about advancements in gas and use technologies as a potential way to reduce greenhouse gas emissions. They thought there was a lot of potential for that. Nobody had really looked at it. So that was phase one, was what technologies are out there for reducing GHG emissions from use of natural gas, more from an efficiency than anything else. And then that was kind of the GHG reductions, the gas consumption reductions, and consequent GHG reductions at the customer level in residential and commercial, small commercial sectors. And then the next year we rolled that up to what would be a reasonable estimate of the national impacts for the United States on the residential direct use sector in buildings. And Natallia will show you how we walk through that, but trying to get some idea to how fast would these technologies penetrate, what were their savings, and what would that mean ultimately for the contribution of the residential residential building sector to GHG emissions. We did take a look also at briefly at the other parts of the gas value chain that could contribute to GHG abatement, which is on the upstream side, obviously with replacing fossil gas with hydrogen or biomethane, biogas, and also looked at reducing methane leakage around the natural gas infrastructure, but we did not analyze those independently. Just a bit of background for those of you outside the US, as in Northwest Europe, I would say natural gas is the dominant space and water heating fuel for all the US except the South. And on peak cold snap days in the winter, gas is supplying over 85% of heating energy in the US. So that's not a surprise, but just to remind everybody, we have a very large and valuable infrastructure for gas delivery in the US. One of the things we try to do was supply some facts around how you could leverage that infrastructure for some continued benefits in decarbonization, rather than retiring the assets early and electrifying everything, which is the policy trend in some I know some of the Western European countries and in parts of the US also. Another background contextual fact, how big are residential direct uses of natural gas as a part of the US total. If you do the math, the breakout pieces of the pie chart is the residential building sector. And then it shows you the fuel breakdown between petroleum, electricity, and natural gas. The natural gas now provides about 27% of building energy use. And if you do the math, that's 3.8% of total GHG emissions in the US as of 2020. Is expected to grow a little bit, actually, according to EIA, Energy Information Administration, by 2040, excuse me. And the emissions reductions overall are expected to be reduced by energy efficiency and fuel switching from more intensive to less GHG intensive fuels. So with that background, I'll turn it over to Natallia to walk through how we approach the issue and the steps in the analysis. Okay.
Thank you, Bill. So as Bill mentioned, there were 2 phases to our project, which were split between 2 years, and the scope was slightly different, but I'll explain. There was quite a bit of continuity between the 2, and I'll point out what the differences were. Basically, the objective for the first phase was to identify different technology, innovative technologies for end use in the residential and small commercial sector of the that use natural gas, and see what their impact could potentially be at a high level. So the first phase was a bit more qualitative, as we were trying to identify all potential relevant technologies, and we kind of did it in 4 steps. First, we work with Gas Technology Institute, which pretty much spends 24/7 around the clock just thinking about these technologies and pushing them forward and seeing which ones are more promising. And together with them, we identified, as you see in the first column, the 12 areas of innovation or innovative technologies that we can look at. Like, for example, condensing technologies was one, hot water heating and boilers was another one, things that are related to cooking and kitchen were the third one. So just a few examples. And within each of these innovation areas, we identified potential technologies that currently exist today. They're currently in maybe piloting or development phase. So we tried to look, I think our cutoff was, if it's potentially that's something that could be commercialized by 2030, it's in. If it's beyond 2030, then it was out. And we identified close to 100 different technologies. And then we looked, what you see, this honeycomb is essentially what are all the end uses and pathways that this technology can be relevant for. So we identified 7 end uses and prioritized 26 different technologies. And we try to look at not at just how sustainable each technology is, but what kind of value generally it delivers to the customer. So affordability, what's the cost, sustainability, or what's the overall energy efficiency potential or potential to save greenhouse gas emissions, resiliency and comfort were there as well. If we could go to the next slide, you see the end uses that we identified and corresponding technologies that we prioritized. As of right now, I'll just give a few examples and I'll explain how we did the prioritization on the following page. But basically, as I mentioned, no, let's go back to the previous for just 1 second. You see that the areas, the end uses that we looked at generally was the building energy management, think things like building envelope and being able to, with smart thermostat, control how you manage the energy usage, cooking, heating and water, and heating and cooling of space, water heating, cogeneration, so think micro CHPs, and laundry. Transportation, we only briefly looked at. It was not, as you can probably imagine, it's a huge, a whole other area that deserves probably 2 other projects. So it was not, we just looked at it for comparison purposes. We didn't really include any of those technologies in our research. And we did similar for small commercial, and we're a little bit of a difference between the 2 as far as the most applicable types of technologies. So if you go into the next page, you can see how, as I mentioned, this phase was a bit more qualitative. We needed a way to quickly prioritize without doing the detailed quantitative analysis each of the technologies, and we really looked at this 6 criteria. First, how are you able to impact the energy consumption and greenhouse gas emissions? And the second, how mature is this technology? And we really emphasize something that could be commercialized in the next 5 years. Our thinking here was, if it's something 10, 20 years from now, we're probably not even going to have natural gas, or natural gas might be replaced by biofuels or hydrogen or electricity, you name it. But what we're really interested in is something, if it's mature enough today or in the next 5 years, that you can reduce greenhouse gas emissions today, while you're still trying to figure out what you're going to replace the natural gas with. That is where the real value is. So that's why maturity was such an important criteria for us to prioritize these technologies. And the other 4 were just other non-energy benefits, like water usage, what the cost is, what's the regulatory and commercial barriers that may prevent adoption of technology, and how quickly you're able to scale something or to standardize it to be able to fit into existing homes. You can go to the next page. On the next page, at a high level, you see, I think you skipped a few. I need page 10. Yep, thank you. At a high level, these are high level potential for decreasing the usage in each of the highlighted end uses here. So this is just, again, meant to give you at a high level what is worth looking at. It's looked at, like, for example, up to for heating up to 55%. We took just one end use and looked at absorption heat pump only, and looked at research papers and tried to figure out, okay, what is the maximum potential? Obviously, when you implement it, depending on how old your pipelines are, how insulation works, that maximum percentage, or, as looking at previous presentation, what your behavioral tendencies are, that could be significantly reduced. But this was a high potential and a way for us to prioritize the technologies. So we can go to the next one as well, and I'll probably skip the next slide or just pause it briefly. It's the same view, it's just for small commercial sector. And if we get to the slide number 12, I think, the interesting thing here, we get, okay, what do we do with these technologies now? And that's where we get to phase 2. In phase 2, we, now that we've prioritized interesting technologies, we developed these 3 scenarios. And we selected really 1 or 2 at most technologies. And we know in reality, there are probably, in real world, there are probably going to be a lot more. But for modeling purposes, we just wanted to select 1 or 2 that are really representative of what's going to be in the real world, that we can measure the impact. So the first scenario, and I guess I should quickly mention that the base scenario for us was what was currently forecasted in annual energy outlook, which DOE produces every year, given existing policies, which, obviously new policies change every time, every year. So the base case for us, though, what was forecasted given the policies currently in place. Scenario 1 was what happens if we accelerate adoption of near-term high-efficiency technologies. Scenario 2 was even higher acceleration, and we included newer technologies as well. What happens if they mature faster and the penetration rates are higher? And the third scenario was essentially the same as the second, but we also tried to look at, okay, what happens if we can also introduce RNG or renewable natural gas what kind of impact to the greenhouse emissions you would have. Yeah, we can go to the next one. Quickly wanted to note that in our base case, there is a natural reduction of energy consumption just because the efficiency standards that are currently placed are over time tighten up, and you replace your old inefficient furnace with a newer one, and if you place it 15 years from now, it's even going to be better. So even with existing policies, we know that energy consumption will be decreasing for most end uses. We also know that there is a little bit of fuel switching going on. So for example, there are still households that use heating oil or kerosene or other dirty fuels, fossil fuels for heating and things, and both space and water heating. And a lot of times that gets switched to natural gas. So there is increasing number of households that use natural gas, but decreased energy consumption per household. And in absolute terms, there is a decrease across the key end uses, which are for us as space and water heating. There is a small uptake in dryers, and that's just primarily because there are more dryers that use natural gas over the course of our timeline. So on this page, you can see our technologies that we selected and their efficiencies. And because space heating is by far the largest end use, I'll just highlight that one row, which is the first one. For scenario one, we use natural gas furnace, which is 97% efficient. And for the second and third scenario, we use the same furnace. And we also looked at gas absorption heat pump, which is natural gas heat pump in essence, which is a technology that is currently in piloting phase. But if you go to your local home improvement store, you probably won't be able to get it today, but hopefully you will in the nearest future. So we can go to the next page. I'm only very briefly, given the time, pause on this. This is a high-level description of the model that we built and where the inputs came from. Basically, we try to rely on things like census that provides the data every 10 years or so, EPA, which is Environmental Protection Agency, GTI, which is the Gas Technology Institute, which help with modeling specific pieces of equipment. And we take all of these inputs and we develop two modules. One is equipment usage module, which we basically try to estimate, given the climate area that you're in and the type of house or dwelling that you're in. And I think we had 5 types of housing dwellings, everything from single family home to mid-high rise or like apartment buildings that have more than 20 units or so. And we try to forecast, given the heating degree days between now and 2040 and what's the requirement is going to be for each region, how much you'll be using that equipment to provide space heating for you. And the other module was basically looking at the penetration. There is an existing equipment stock, and we assume that it's essentially a bell curve distributed furnaces that primarily used in stock today. And we know it's simplification, not everybody uses a furnace. But for the purposes of the model exercise, we assume that they do. And we we model the penetration of these new, more efficient end-use technologies. And the output was basically what is the energy reduction and what's associated greenhouse gas reduction as well. And we did look at things like if I'm using, for example, electricity in California, my greenhouse gas electric footprint is going to be very different than if I'm somewhere in Texas, just because the generation mix for electricity is different between the two states. So we can go to the next page.
Real quick, about 2 minutes left.
Thank you. I'll try to super fast accelerate this so Bill could wrap up and present the results. We did look at things how the cost of equipment would change, and the primary drivers are always the scale. If you can reach the scale, then you can get cheaper equipment. If you cannot, it will not drop in price. If we go to the next page, we also played around with incentives. We assumed residents will be rational in their decisions, which means they always go for the cheaper choice. So the way we offset the cost, the capital cost, is basically adding more incentives. And if we look at the next slide, we used a penetration model, which is again based on rational decisions of our natural gas consumers, that tells you, depending on how large your payback for each specific technology, that's going to impact your essentially S-curves. The quicker the payback, the faster that technology is going to penetrate. So with this, I'll hand it over to Bill for the results.
Thanks, Natalia. So that was one trick there. We used a penetration model to get a realistic estimate of how quickly you could achieve reductions. And we also designed subsidies to be smart to expire after the necessary scale economies that have been achieved. Just I won't go over these for sake of time, but as you might expect, the volume of reductions was highest in the colder states that were heavier gas users. Assuming rational economics, to quite high penetration of more efficient gas heat pumps, a very high penetration of gas water heat pumps, and significant savings. And these savings, by the way, do include the cost of the subsidies. So it's the total social cost, well, the total direct social cost to the consumer and to the whoever's paying the subsidies. Basically, we're not ignoring the subsidies. As you might expect, given consumer behavior, the first cost was really the key driver of reducing the first cost was the most important thing to increasing penetration. Headline number here, basically, by 2050 in the high penetration scenario, which has the somewhat newer emerging technologies and more aggressive subsidy programs, you can reduce residential end use carbon emissions in buildings by 40%. Purely through energy efficiency penetration, economically rational energy efficiency penetration by 2050. So that's not an inconsiderable number. And now those numbers sector-wide are achieved despite the fact that you have a lot more units out there. So there's much less consumption per individual. This one we could talk for a long time about. This is one that we two abatement curves of sort of the in the residential building sector again. What are your gas and electric options for reducing GHG emissions, and how much do they cost in total? As you can see, the gas pathway is significantly cheaper and quicker for that matter, because you have a lot of building stock turnover and expensive retrofits and so forth on the electric side if you're going to try to do it through electrification of space heating. This big blue block here is the assumed cost of policy-driven electrification if you're not using a backstop technology of direct air capture, building, the building retrofits and the building new electrical supply and tripling the size of the T&D system on the electric systems is very expensive compared to most other options. This kind of just repeats what I said on the gas side. Because you're using existing infrastructure, you're not doing a lot of building retrofits, you can accomplish the reductions much more quickly and cumulatively over time, achieve faster results for less money. So this kind of summarizes over the past, we've been talking about the the last part of this gas value chain, the demand side, in order to get to the 90% goals of GHG reductions, you would need obviously to pair that with reducing methane leakage and greening the gas supply too through biomethane and hydrogen. There's been a lot of talk about that at this conference, so I think that'll be probably the main topic of the policy debate. But we thought it was at least worth pointing out that there are a lot of low-cost gas GHG emissions to be had through using rational sort of smart subsidies to increase the penetration of more efficient gas technologies. This was a joint project really of GTI and Roland Berger. And that's it.
Great, thank you, Natallia and Bill. Let's see, we do have a few minutes for questions. So who has questions for both of these folks? Well, I can kick it off with a question. I know the whole kind of motivation of this was greenhouse gas emissions, but there's local air pollutants are still also very important. I'm wondering if you've done any kind of a similar analysis looking at those local air pollutants and how both the levels and kind of the distribution of those might be changing as we change efficiencies and fuel sources and all that kind of stuff.
Yeah, no, we didn't, Matt. That's a good, another, I guess I would argue, secondary benefit and probably a declining benefit over time as the electric system is cleaned up and you have less coal-fired generation to displace. There is an indoor air quality issue too that some of my colleagues in the environmental movement are raising as far as the effects on indoor combustion of natural gas, and have you considered those adequately? So that's a fair point.
I'll proceed the question. Nor did we explicitly include upstream emissions, which could mean getting it from under the ground, methane emissions from under the ground to the end use. We only consider our boundary was only around actual end use in homes, which not could be mitigated. There are several ways to mitigate it fairly effectively, but not fully taken into account in the way we've done the study as well.
Thanks. Maybe one more question for Natallia and Bill. Okay, well, once again, I'm sure they're happy to take questions and comments offline. So feel free to email or you can always chat them through Zoom with those questions and comments. And so with that, we'll move on to our final talk of not only this session, but of the entire conference. We've got Mushi Yang closing us out here. So she's going to be talking about targeting energy efficiency program design.
Thank you. Did my slides came up okay? Can I get a nod?
Yes, looks great.
Great, thank you. So hi everyone, my name is Mushi. I'm a PhD student at Cornell University. In this paper, which is joint work with Professor Todd Gerarden, we study how to improve the design of behavioral interventions to maximize net benefits. So we do this in the setting of home energy reports, also often referred to as O-Power letters. It is a widely adopted program in the US and I believe across the world as well. In the US in particular, it has served over 6 million households and the estimated annual cost is over $1 billion if this program is scaled up nationally. So I think it's important that we think about how to maximize the cost effectiveness of this program. So in this paper, we studied the optimal assignment of home energy reports. We utilized a recently developed policy learning algorithm from the statistical decision literature to search for simple treatment assignment rules. And we also quantified the potential gains from targeted treatment. So quickly, some background on the OPOWER program. In this program, households typically receive information treatment in the form of letters. So here is the sample letter. On the first page, we see a comparison of historical energy usage with the usage of efficient neighbors. Both in numerical terms, we see 3 bars here: efficient neighbors, your consumption, and the average consumption of average neighbors. We also see a comparison in terms of either a smiley face or a frowning face, depicting like whether you use more energy compared to efficient neighbors on average or less energy. We also see information about, well, some tips on energy conservation, and also information on rebates or subsidies available on energy efficient products that could also lead to energy savings. So this information remind households about how much energy they can save, and also might induce some peer pressure or moral persuasion that nudge households to engage in energy conservation. We obtained data on the Home Energy Reports program implemented in a northeastern state in the United States. For each household in this state, we observed monthly electricity consumption, the original treatment status in the OPOWER program, and we also have a snapshot of household characteristics, which are relevant for energy consumption. So in particular, we have income, number of household members, marital status of the head of the household, square footage of both the unit and the building, and finally the year of construction of the house. So we'll use the average pre-treatment consumption, the average post-treatment consumption, and household characteristics in our analysis. All the data are at the account level with about 50,000 households in the estimation sample. We'll utilize cross-sectional variation across households in deriving treatment rules. In the interest of time, I'll just highlight that the program was implemented with the RCT design. There were multiple waves of RCTs over the sample period, each with its own treatment and control group. In the pooled sample, about 70% of the households were treated. So this event study figure shows the treatment effect in each month before and after treatment assignment, controlling for observable household characteristics and also month by wave fixed effects. So we can see that after the initial report, households reduced energy consumption, in particular electricity consumption, by about 1.2%, and this effect is persistent over time. So this shows that the program drives energy reduction on average, but behavioral channels are complex and people's response to the treatment might be heterogeneous. Some people might even increase consumption after treatment. So after we quantify the causal impact using the initial RCT, we can do better by targeting treatment to the types of households who might be more responsive and avoid treating households who might respond negatively. Before we think formally about who should receive treatment, we present some motivating evidence that there is indeed heterogeneity in the treatment effects in this data. We estimated a triple difference model where the below median and above median indicator for a given covariate is interacted with the treatment dummy and the post-treatment dummy. This table shows that the treatment effect for 4 observable characteristics, we can see that the treatment effect is larger for households with higher baseline energy usage. And also, based on point estimates, households with larger houses and higher income also reduce consumption more, but the difference is not statistically significant in those 2 cases. So with this suggestive evidence, we now turn to think about targeting treatment based on observables. The formal question we study is how to use targeted treatment to maximize the net benefit of the program. We follow a method called empirical welfare maximization to empirically search for a rule that uses pre-treatment characteristics to assign treatment in order to maximize gains in the target population. The value of a rule, which is denoted as pi, can be defined in potential outcome terms. It is proportional to the expectation of potential outcome y1 for those treated and potential outcome y0 for those not treated. Then we can rewrite this value function as the baseline value without treatment and the value gain relative to it. Under some important assumptions, which are valid in our RCT setting, the value gain part can be rewritten using the inverse propensity or probability weighting estimator, which is equivalent to a difference in means estimator in this RCT setting. Now, solving for the value maximizing treatment rule is equivalent to solving for the rule that maximizes the average value gain. The idea of empirical welfare maximization is solve the sample analog of this problem within a constrained set of candidate rules. In the context of energy conservation, we transform the original maximization problem into a minimization problem shown here. The objective function is exactly the same as we saw before, with the outcome variable defined in terms of either energy use or energy cost. The last part of this optimization problem is policy constraints. We consider a two-dimensional characteristic space and two policy classes. The math is not important here. I just want to highlight that first, for quadrant rules, we basically need to solve for two treatment thresholds and two treatment directions. And the second types of policy class is linear rules with cubic terms, which allows more flexible partitioning of the characteristic space. You might notice that even though the concept is quite straightforward, this optimization problem is quite challenging to solve since it is non-continuous and non-convex in pi, our treatment assignment. So the conventional methods don't apply here. We use two separate approaches to solve this optimization problem. For quadrant rules, we use grid search. And then for the cubic rules, we transform the original problem into a mixed integer linear programming problem and use the simplex optimizer to find the solution. Okay, so now let's look at the treatment rules we found. As an example, first on the left, I'm showing the quadrant rule that minimizes energy cost in the income and pre-treatment usage space. By this rule, we should treat households with income above $70,000 per year and pre-treatment consumption above 700 kilowatt hours per month. This rule is shaded in red. Obviously, it is particularly easy to visualize and also implement in practice. On the right, I overlaid cubic rules in blue. This cubic rule shows that it generally agrees with the quadrant rule, but it allows more flexible treatment boundaries on both dimensions. So what are the gains from targeting using those rules? The final column in this table shows the energy savings relative to the average treatment effect on the treated in the original RCT. And I should mention that the average treatment effect on the treated is about 3.63 kilowatt hours per month. So we can see that in terms of energy reduction achieved, all the EWM quadrant and cubic rules outperform random assignment. And some cubic rules even double the savings. And the difference is statistically significant. This figure, instead of the numbers, I show the EWM savings in this figure for cost savings. Again, the RCT saving is normalized to be 0 here. The quadrant savings are the cost savings for quadrant rules are shown in green, and the cubic rules are in blue. So we can see that compared to random assignment, again, all the EWM rules achieve higher cost savings. And in fact, the cost savings are an order of magnitude larger than the effects of the RCT. Demographics data is often only available for a subset of households. So how about we only use pre-treatment consumption data in targeting? Do they still perform well? Here, I'm comparing the two-dimensional demographic rules that we just saw in the previous slide with the one-dimensional rule based only on average pre-treatment consumption, which is shown in red here. So we can see that the one-dimensional rule achieves almost the same level of cost savings as the demographics rules. Those three sets of rules on the right are based on minimum, maximum, and standard deviation of pre-treatment consumption. They also perform at least as well as the rules based on demographics. So in this setting, pre-treatment consumption is the most important determinant of optimal treatment assignment. And targeting using electricity consumption data alone can overcome the data limitation and avoid the uncertainty associated with imputed demographics data. And finally, I want to highlight three important properties of the empirical welfare maximization method. First, it has been proven theoretically that the derived rules are regret optimal, meaning that they achieve maximum value within the policy class at a theoretically optimal rate. So no other rules in this policy class can outperform it. Second, because we solve for rules that maximize the average value directly, we don't need to estimate all the causal effects at the household level. So this is advantageous in situations where we cannot guarantee to efficiently estimate causal effects. And finally, learning the treatment rule and conducting inference on the associated gain is an integrated process using this method. So we can derive valid confidence intervals using this method. So with that, I want to conclude. We use a policy learning algorithm to provide empirical evidence on the potential gains from targeted assignment of home energy reports. We find that using transparent and easily implemented treatment rules can yield significant gains relative to random assignment in terms of both energy savings and cost savings. And finally, the gains from treatment rules based on electricity consumption alone is significant, which demonstrates and underscores the performance of simple rules in this practical setting. So with that, I want to thank you for your attention, and I'm happy to take any questions.
Great, thank you, Mushi. Do we have questions for her?
I have one. I just as it may be outside the scope of what you were thinking about, but there is an increasing need to pay attention to when we may want to encourage consumers to consume more electricity as you get high renewable generation peaks and so forth, and you're trying to get customers to shift their loads into the period of high renewable generation.
Yeah.
What are your thoughts about how this might be used to inform, classically that would just be through time of use rate design or something like that, but there may be other measures that could be taken.
Yeah, thank you for your question. So yes, so in this study, there is one unfortunate data limitation is we only got electricity consumption data in terms of kilowatt hours, not demand data in terms of, or even high frequency kilowatt hour data. So if we have that type of data, then we can absolutely apply this method to target the type of households, to actually target households to reduce peak demand so that we can maximize the social gain. So we can really reduce peak demand and reduce those marginally, those very highly polluting power plants operating in peak demand hours. So I think this method actually has a lot of potential if we're fortunate to have more detailed high frequency data on demand.
So I have kind of a, I don't know, this is kind of a half-baked question, so I apologize in advance and feel free to punt if it's like way beyond the scope. But I mean, it's always struck me with these O-Power studies that essentially what's underlying all of this is the idea that homeowners are not able to optimize their energy consumption before the intervention, and then afterwards this new information allows them to better optimize. And so I guess I'm wondering if knowing who responds based on the various metrics that you used could help us learn something about who it is that is like better at, or like, I guess just like how households energy use optimization, like their internal behavioral heuristics or something like that, how that differs across these same metrics. Like if we're seeing the big users are the ones who respond, that would imply they must be the ones who are most misoptimizing to begin with, or something like that.
Yeah, there's a very like big literature. Well, to me, there's quite some studies that look at mechanisms behind those behavioral interventions. You know, those behavioral responses, whether households reduce consumption because they feel the peer pressure, or they feel they have a sense of like social responsibility, or they have a moral responsibility. So yeah, and some households might even only respond to the rebate information. So we see they have like big drops in energy consumption after the letter, but that's because they invested in a new efficient heater. That's very distinct from the being more conscious at turning off lights more often. So yeah, it's very complex. I think the mechanism behind those average treatment effects, or even the heterogeneous treatment effects, is very complex. And in this study, we only used a 2-dimension. We only study treatment assignment in 2 dimensions. There could be a lot more dimensions that explain households' behavior, and potentially, and I think there are studies that are also at this point also looking at using machine learning methods, to first select the dimensions that we should focus on if we have more data, if we know about something about their environmental consciousness, so that we can derive more detailed or targeted assignments. Yeah, but yeah, this is like very exciting. So because it's very complex, I think it's very interesting and exciting work to me. Yeah.
Thank you for.
Thank you.
I think answering a question way better than I asked it.
I guess I have a follow-up question, if I can. You just mentioned it, but I am interested in because you mentioned that in the letters there is this information about also which type of energy efficiency installations or policy, well, not policies, yeah, basically measures they can adopt. Yeah. Do you have a sense, and the RCT runs from 2013, 2018, I understand that you have information of how many households could engage in installing this type of renovations, energy efficiency renovations?
Yeah, so the information treatment, the O-Power RCT ran from 2013 to 2018. I also have data. So in that particular state, there were also like rebates available on energy efficient products that you just mentioned. But I only had data on those rebates from 2014 to 2015, I believe. And we looked into, whether households, after they receive the letter, whether they invest in something else. There's a very weak link. Probably because we don't have enough data. We only have 2 years of installation data. So yeah, I would be very, very interested in getting more data and then looking into this, because I do believe like those behavior responses could be very small compared to the actual installation base, the savings driven by the more efficient technologies. So yeah, yeah, if there are more data, then I would be very happy to look at that in more detail. Thank you for your question. Yeah.
And just a comment to follow up on what we were just saying, Mushi, that if you look at the statistics on the average cost per kilowatt hour saved across the tight range of types of energy efficiency programs, the behavioral change programs are a lot less costly. It's just much more scalable because it's information technology. So
yeah.
Good work, and I think this avenue of as you get more data, as you were saying, from smart home appliances and smart thermostats and things like that, you should be able to target the behavior change measures more productively.
Thank you. Yep.
To follow up on that, this isn't a question for Mushi per se. So maybe we're transitioning into just the general discussion portion to end our session here. But another thing that's always struck me as interesting about this O-Power literature is like what Bill was saying, is that it's these behavioral changes that are actually really pretty efficient because they're cheap. And they're cheap in terms of the cost to the government or to the utility or something like that. But we always kind of ignore the fact that like the customers themselves might be getting a huge welfare hit because we're shaming them into better behavior or something like that. And so that obviously goes beyond the scope of what we can really measure well, but there could be all kinds of like unobserved costs running around in the background here that get really tricky to think about the overall welfare effects and costs of these policies.
Absolutely, yeah. Hunter Alcott and I believe Alcott and Kessler, they have a paper in AER, looking at the social welfare of home energy reports or information provisions. And I think one of their findings is that those non-energy costs associated with the reports would reduce overall welfare by at least a third. So it's important when we evaluate the welfare impact of these programs to take into account, because a question I often get is, if I reduce energy consumption, then my utility would drop, because that means I have to turn up my air conditioning setting, so that to me my comfort level drops. And so consumer welfare could decrease, but we need to weigh that against the environmental externalities and stuff, and also take into account non-energy costs. Yeah, another limitation of our study is we couldn't get a reliable estimate of those non-energy costs. So we're not claiming welfare impacts from targeting, but only like private energy cost from targeting. Yeah, but I think the point you raised is very important to consider. Yeah.
Yeah, if I remember right, I think one of those Hunt Alcott papers found that there were some customers that were actually willing to pay to not receive O-Power.
Yeah. Exactly. Yeah.
All right. Do we have any other questions or comments for any of our presenters, or just about energy efficiency generally?
I would just hope the policymakers recognize it's the low-hanging fruit. They should go after. Amory Levins is right.
Yeah, absolutely. Well, then why don't we go ahead and call it a day there. Thanks to all the presenters for a great session. Thanks for the attendees who came. Thanks to everybody asking questions. And yeah, I hope everybody has a great summer, and we can see one another in Paris next summer.
Yeah.
So take care, all.
Thank you.
Thank you.
Bye.
Bye.
Bye.